Welcome, everybody. This is statistics. It is lecture 13. Let's see if I can get that focus. Just right. Okay, so we're going to be talking about hypothesis tests today. And I want to start by going back and watching a movie again. Sorry about that. Sorry for the advertisement. I'm going to skip ahead just a little bit. Probably could have skipped ahead more. Now I'm worried I'm going to miss the line. All right. So if you remember on the first day, we talked about how Dorothy is a statistician. And specifically in that clip, Dorothy conducted an informal, yet still statistical hypothesis test. Maybe the general description of what a hypothesis test is, and we're going to get into a formal process for that. Hypothesis test starts with a question about the world. All right, so in Dorothy's case, that question is, am I still in Kansas? A hypothesis as to the answer, a hypothesis about the correct answer, gathering some data, and deciding if the data supports a specific conclusion. At the root of it, that's what a hypothesis test is. We do that every day. Dorothy did it. She woke up. She was wondering, where am I? Am I in Kansas or am I not in Kansas? That was the question. Her hypothesis was, well, I either am or I am. I'm not. Then she gathered some data, in this case, looking around at all the flowers in the yellow brick road. And she decided that the data supported the conclusion, I have a feeling I'm not in Kansas anymore. You've already done informal hypotheses tests in your labs. For example, A group of 25 patients have 18 diabetes diagnoses. Is this group representative of all patients? Right? There's a question about the world, which is this group of patients representative of other ones? There's a hypothesis, yes, they are, or no, they're not, right? That's what you think the correct answer might be. The data is, well, 18 out of 25 of them have a diabetes diagnosis. And then using a binomial distribution, you concluded, oh, 18 out of 25 is very unlikely. So I have evidence that this group is not representative of all patients. And if you want an exercise, you can, if you worked on a different data set, you can think about how your binomial probabilities question was an informal hypothesis test. Another one, the Southern Cone countries, cities. The Southern Cone refers to Brazil, Argentina, Chile, Bolivia, Paraguay, and Uruguay. With this southern, and it's a cone. Anyway, the Southern Cone cities have an average precipitation of about 125 millimeters in April, compared to about 100 millimeters in all cities. The question is, are the southern, in all cities in the Americas? I think that's what was the actual data. Are Southern Cone cities representative of all? Here by American, I mean the Americas, not the United States America, right? Of all American cities. And you concluded, well, the probability of seeing a group of 30 cities with a precipitation of 125, if the average really is 100, that was like a 2% chance. So it's very unlikely that the Southern Cone cities are representative of all American cities. You conduct a hypothesis test. It wasn't super formal, but it was a good statistical hypothesis test. Now, one reason I'm going to teach you the formal approach is because that's generally expected that students know how to do it very formally. But what's more important for me is the fact that you've been doing this since day one. You've been formulating a question about the world. You did it with Dorothy. You've collected some data, and you've used that data to decide what do I think the answer to that question is most likely to be. Let me do another example. Here I'm going to do an informal hypothesis test, but I'm going to put a few more numbers on it. Suppose that research indicates, this is a phrase I like to use, doesn't mean that it's high quality research, doesn't mean that it's extensive, doesn't mean that it's academic or rigorous, but suppose that research indicates that the average weight of cats in Salem, in Salem, is 10 pounds. You wonder if that's true. What are the possible answers to that question? If it's true. Yeah, two possible questions. Possibility number one, what we call our null hypothesis, is yes, the average weight is 10 pounds. Now, suppose it is true. Is there anything interesting going on in Salem? In regard to the average weight of cats? No, right? If Salem is the same as everywhere else in terms of the average weight of cats, we say, okay, cool, moving on, studying something else. I'm going to call this very informally, I'm going to call this the boring result because there's nothing more to do. If the average weight of cats in Salem is 10 pounds, you're done. You got to study something else, maybe dogs, maybe cats in Eugene. I don't know, but you're not studying cats in Salem anymore. You got to find something else to do. And the other possibility, what we call the alternative hypothesis, is no, the average weight is not 10 pounds. That's an interesting result because now you get to ask a very specific question. What question do you ask if this is your answer? Why? What is the actual? Okay, that's a good one. I thought you were going to say why, so I said why. The interesting question from a scientific perspective is why? Now I get to learn more about cats in Salem. I don't say, well, they're the same as everywhere else. I say they're different. Why? I get to do more research. My interest, my curiosity, I must have had some curiosity if I asked that question at all. Now I get to satisfy my curiosity a little bit. So this is the interesting result. This is a very informal way of thinking about your two possible hypotheses. How do statisticians make decisions? What do we use to make decisions? Yes, good. Data, absolutely. We're going to need to collect some data. Yep. Before we get there, because I want to lay out kind of our process, the one that I think is a good one to follow. When we make a conclusion, we make a conclusion based on probabilities, right? Statisticians ultimately make their decisions based on probabilities. Data helps us make a decision. The decision itself is made using probabilities. So we want some sort of probability that's going to tell us if we're in the boring world or the interesting world. What might be a good probability for that? What would be a good cutoff? Think back to your labs. Think back to these questions. How did you decide that the group was not representative? How did you decide that the Southern Cone cities weren't representative? You looked at what? Exactly. You looked at the probability of observing it and you said it was less than 5%. So we're going to choose a probability cutoff. I'm going to close the doors here. We can choose whatever we want. We could choose 1% or 10%. But as a default, let's choose 5% because that's what we always pick if nobody tells us otherwise. .5% or 0.05. Now let's go out and collect some data. Let's weigh 36 cats. randomly selected. That's important. We have to have a good methodology if we're going to trust our data. Suppose that the average weight, so the sample mean, is 12 pounds. And the sample standard deviation, right? Whenever you collect a sample, we like to have some summary data, and good summary data is the sample mean or the sample standard deviation is, I bet I can make this work. Yeah, 6 pounds. I don't want to use 6. Sometimes when you pick numbers, the numbers can end up being confusing. I'm going to pick, let's see, is it still going to work? 4 pounds. There we go. So this data here, 36 cats with a sample mean of 12 and a sample standard deviation of 4 is like Dorothy's Technicolor flowers. This is the data we're going to use to compare to what we expect. And the way we compare it is we compare sample mean X bar to what we would expect, which is the expected weight of cats, which is 10. This is going to be a visual hypothesis test. We know that the sample means X bar are distributed normally. We only collected one sample of 36 cats because we don't have all day. We can't go out and do that 100 different times. But we know because of the central limit theorem that whatever sample we did collect should come from this type of probability distribution. And what's the center of the probability distribution? What's that value there? No, actually. 10, because we're assuming we live in Kansas. We're assuming we live in the boring world. So this is X bar if we live in a boring world. 12 is a great guess. And in fact, you can do this exact same hypothesis test centering it at 12 if instead you build a confidence interval. A hypothesis test and a confidence interval are two sides of the same coin. We've got a standard deviation because any normal distribution has a standard deviation. How wide should that standard deviation be? It seems like it should be 4. But again, because we're dealing with X bar, we're dealing with sample means, it's going to be spread out much less than our actual sample would be spread out. So we need the standard deviation of X bar, which if you remember, do you remember the formula for that? You have to take the square root of the sample size. You divide your standard deviation of the sample by the square root of the sample size. You shrink it down because we're doing good statistics, so we collect more data. So it's going to be 4 over the square root of 36, which works out to be 4 over 6, or let's do 0.7. It's really 0.66666 forever, but this is going to work for us. And again, this is one of the hardest conceptual things to click in. That's okay. To realize whenever we talk about sample means, we're given a number like 4 pounds, but that's not the number we end up using. We always have to change it to be the standard deviation of our sample means. So that's 0.7 and another 0.7. That's going to get us to what? 11.4 right here. Or the other way, it was going to get us to 8.6 down here. What that means is in a boring world, we would expect almost all of our samples to have an average between 8.6 and 11.4 pounds. We wouldn't expect them to be exactly 10, but we'd expect almost all of them to be within a pound and a half about of 10. What was our sample mean? 12. Oh, it was way out here. What do you think? How likely is that? Very likely? Very unlikely. This is very unlikely in a boring world to have seen 12 pounds or more for my sample average. One of the nice things about the normal distribution, the central limit theorem, is we can make these comparisons using step sizes, right? If we're more than 2 standard deviations away, we generally say we're not living in a boring world, we're living in the interesting world. But again, statisticians make their decisions using probabilities. So what we really want is we want a probability that comes along with this 12-pound average. And so for that, we use technology. To get the probability of observing data more extreme than what we actually have, we use technology. So the first technology we're going to use is our app for visualizing normal distributions, because that gives us some probabilities in there as well. There it is. Okay. So we're building a normal distribution in the boring world. So what's the center of that normal distribution? 10. And the standard deviation is of the sample means. So it's not going to be 4. What's it going to be? Yeah, 0.7 or 0.667. If you're going to be picky later and wonder why I didn't be more accurate, I'll use that one now. There's our distribution. And there's 12. That's way out in the tail. So even just looking at it, we can say, yeah, that's not very likely. But if we want to do a more formal hypothesis test, we're going to actually collect the probability. So we're going to go outside of a region. And our right boundary was 12, because in our hypothesis test, we just thought it wasn't equal to 10. So it could have been more, it could have been less. So I should also put a left boundary on there, which would be 2 steps or 2 units below, right? That'll give me a nice symmetric area. Can't even really see it, but it is shaded in here and here. And there we go. The probability, remember this decimal here is actually a percentage, a decimal of a percent. So that's 0.27%. The probability of an X bar more extreme than 12 is 0.27%. So that's 0.0027. Or 0.27%. And as Bella said, that's very, very unlikely. Is this a likely event in a boring world? Nope. It's like Technicolor flowers in Kansas? Well, unless our data was bad, we don't live in a boring world. And we're statisticians, so we're going to trust our data. So we reject the null hypothesis in favor of the alternative. We conclude that the average weight of cats, at least in Salem, is not 10 pounds. It's probably more because that's what our data said. We don't have to say it's 12. We don't have to be that confident. A hypothesis test is not about saying, I think it's this answer. A hypothesis test is actually about saying, I don't think it's the boring answer. Now we get to ask just a few more questions. And you probably wouldn't have ever seen these next questions if you didn't take this class from me, because this is partly my experience working as an epidemiologist, working in statistics. But it's becoming more and more common to ask these additional questions. So hopefully, if this video stays up for a while, it will no longer be a correct statement. But we should ask, does it matter? Which is another way of saying, is this result practically significant? And what ethical significance does this result have? So you might say, well, yeah, it's 12 pounds instead of 10. That really doesn't make a difference, right? That's not a big difference in a practical sense. Sure, it's unlikely to have seen it, so it's statistically significant, but it's not actually meaningful for the lives of most cats in Salem. And then you say, well, okay, I guess I'll study something else. I happen to think probably a 2-pound difference in the average weight would be pretty practically significant for cats. I mean, we're talking about 10 pounds versus 12. That's a whole 20% difference in their weights. And the heavier cats are, the more joint issues they have, the more likely to have other health things. Of course, I made this up, so we don't know if it's actually true for Salem. But if that were true, to me, that's practically significant. But you get to decide that as the researcher. Ideally, you're part of a research team. You didn't do this on your own. You worked with some veterinarians. And they brought their experience in to say, wait a minute, it's a 2-pound difference. That it matters. That's practically significant. And then you ask, well, what should we do with it? Right? What does that mean about the well-being of cats in Salem? Should we ignore this? Should we work to change it? How do we change it to improve the lives of cats, et cetera, et cetera? Those are the important questions that statisticians should make sure anybody they're working with does ask. And then the last question is, why is it different? And we get to propose a testable scientific explanation and or, how did I write that? A new research question to learn more. And that's what's usually the best part about being a scientist or being a researcher is when you learn something, it opens up a new door and it gives you an opportunity to study further and learn even more. So maybe it's because cats in Salem are older on average. Do I know that's true? No, but it's testable because I can collect a random sample of cats and find out how old they are. Maybe I just don't have any idea. So a research question doesn't always have to lead to a hypothesis test. A research question can be, what's different about their diets? I'm not saying there's a difference in their diets. I'm saying what's different about it. That's an open-ended research question. And now you're doing descriptive data, right? You learn through the process that cats are eating more food or something like that. But you get to propose a new, either a testable scientific explanation and or a new research question to learn more. Okay. All right. Now I'm going to show you Peter's 10 steps when you want to do a fancy schmancy formal hypothesis test. First, we get a research question. All right, out of ink. For example, historical research, I'm making this up again, indicates that the average height of, let's see, biological male American men is 69 inches. That's 5 feet 9 inches. Is this still the case? All right, there's my research question. Is the average height of adult biological American males in 2026? No, what is, there we go. What is the average height of adult biological males? And nope. One more time. Is the average height equal to 69 inches? For hypothesis tests, yes, no questions are the best. Then we get a null hypothesis. That's the boring possibility. What's the boring answer to that question?
Yes.
Yes, nothing more to learn. Height hasn't changed. Yes, the average height, I'm not going to write the full description, is 69 inches. And the interesting possibility, right? So we would phrase that as a no. The average height is not 69 inches, because now we get to ask why not? What's, let me learn some more about this. Okay. The next thing we do is we choose our probability cutoff, which in statistical jargon is called a significance level. And it's just the probability cutoff. We default to 5% or 0.05. But if your research team wants you to pick a different one and you think it's defensible from a statistical standpoint, you pick a different one. I wouldn't let my research team say, we have an 80% significance level, because that's way too easy to pass. I probably would caution my research team against a 99 or a 0.01% significance level, because we're probably never going to see. Right? It'd be really hard to collect enough data to see a difference. It's important in my mind to choose your significance level before you collect the data, because human beings like to get interesting results. And if you collect your data first and you're like, oh, this isn't very interesting, a little part of almost all humans will be, well, maybe I can fudge the significance level to make it look interesting. I'm not saying we would do that, but for transparency's sake, we make sure that can't happen so nobody else can tell us we did that. So once we choose our significance level, we collect the data. So let me show you the data that again, this is made up. I just generated it. Let's see if I can. There it is. Oh, it won't let me pull it over. Okay. There's our data. All right, I'm imagining that I measured, and I'll write this down on the paper, that I measured 70 adult males, adult biological males in America in 2026, and these were the various heights that I measured. All right, lots of people in the neighborhood of a little bit less than 6 feet. Some people up there all the way at 6'10", some people down there around 5 feet. This again is made up data. It's not completely normal. I built it to not be exactly normal, but that's okay, because when we do these kind of statistics, we're using the central limit theorem. We're asking questions about means, not about individual observations. All right, so my data was 70, n equals 70 observations. And the sample mean X bar, I'm going to be doing this over here on the right side, is 68.8 inches. Anybody have is anybody leaning one way or the other on which hypothesis to go with? .8 inches is our sample mean. What do you think? Do you think the average height has changed, or do you think it's basically the same? Yeah, Alejandra? It sure looks like it. And that's okay. It's okay to kind of say, I think it's going to be this way. But then we do our due diligence and we check the rest of the things. We get a standard deviation of the sample, which is, 4.9 inches. And that tells us the standard deviation of our sample means in the boring world should be 4.9 divided by the square root of what? 70, because that's our sample size. Yep. And I can tell you that is 0.58. Technically, the units are the same. It's still inches. Okay. So now we conduct the hypothesis test, which is a little bit recursive, but this is the way I call it. I say this is the actual hypothesis test. The whole thing kind of is, but this is where we generate that probability. And we can do that visually using the little app. Nothing wrong with that. But as you're going to do in your lab, we can also do it using R, because R is great when we work with data. Here's our, it keeps wanting to put that thing in. There's all the 70 different heights. And we do what's called a t-test on our data, and we put in our hypothesized mean. What do we think the mean is in the boring world? 69. So that's what we put in. It's not the sample mean, it's what we think it should be in a boring world. And this is our output right here. I know it's hard to see from far back, but you're going to be generating it in your labs as well. It's called a one sample t-test. And there's our probability of seeing something more extreme than what we actually saw. I'm going to put it on the paper now. So the probability of a sample mean more extreme than 68.8 inches is 0.7483, about 75%. In statistical jargon, this is called the p-value. I don't think p-value is a very useful word because nobody who hasn't taken a statistics class recently or does statistics all the time knows what that word means. So let's use plain English. The probability of observing a sample with a mean that's more extreme than our data is 75%. Is that surprising? No, because it could happen 3/4 of the time. Right? This is a big probability. This is bigger than our cutoff, bigger than 0.05. There's no evidence that the average height has changed, or not enough at least. I'm going to say no, 75% chance of this data. That's really bad evidence. Okay. So let me write down step 6. I kind of got a little bit ahead of myself. Using some of those formal words here. Step 6 is compare the p-value to the significance level. I got to remind myself of the 10 steps now. Make sure I get to 10. I've got well, we'll see if we get to 10 or not. Collect data should be 4. Oh, yeah. Okay. Yeah. Collecting data is always the hardest part of doing good statistics. So it gets its own. 5 is compute sample statistics. Your sample mean, your sample standard deviation, and therefore your standard deviation of sample means. That's pretty easy when you have technology like R, right? So it's its own category. Collecting data, always the hardest part of doing good statistics, right? Unless you make it up like I did, but then it's not really good statistics except for teaching. So 6 is conducting the hypothesis test. 7 is to compare the p-value to the significance level to decide whether you reject the null hypothesis, like how Dorothy did, where she said, I have a feeling we're not in Kansas anymore. Sorry. Or, and again, this is a statistical formality. Instead of accepting the null hypothesis, we say we failed to reject the null hypothesis. Because in statistics, there's always a chance. So instead of saying definitely I reject the null, or definitely I accept the null hypothesis, we say, well, I can't reject it yet. Step 8 is to consider any possible practical or ethical significance of the results. And in this case, we're going to, sorry, our actual decision in this example is we're going to fail to reject because their data simply was not strong enough. 0.7483 is greater than 0.05. And then we can consider any possible practical or ethical significance of the results. Well, probably none because the results weren't interesting. But there are other times when it would be. Even when you failed to reject the null hypothesis, there might be some practical or ethical significance of that. Say you're spending millions of dollars on an after-school tutoring program to raise the probability that students graduate high school, and then you do a hypothesis test and you say, oh, there's no difference. Well, then maybe you should think about how better can I spend that money to support student learning. That does have a practical and ethical significance, even if it doesn't have a statistically significant difference. And finally, this is 9 steps, it's not 10. You get to ask why. So give a testable scientific explanation. And or propose a new research question. To learn more. And my 10 steps are only 9 this time. And the reason is because I combined the alternative and the null hypothesis into a single step. I remember that now. Okay, so you have you have 5 hypothesis tests. In your lab. One is informal and the other 4 follow these 9 steps. So I would like you to work on those. And you also have confidence intervals if you haven't already started that before then. Next time, just to look ahead, all the subtleties of hypothesis tests. Those subtleties include things like, maybe I don't care if it's not equal. Maybe I want to know if it's more or if it's less. Or, well, what's the chance that I'm wrong? And how can I reduce the chance that I make the wrong conclusion? Things like that. So we're going to talk more next time about those subtleties and investigate it a little bit more. So for the rest of today, I encourage you to work on your labs, get a good jump on those, because those are due in 1 week. You have all the tools to do the rest of that.